I'm sorry? Yes, if you want to hang up, you can hang up. I've already taken attendance. Yes. Okay, so what we're going to be doing, and you can lower your hands now that I've asked the question. We are starting a new unit, and this new unit is like one of my favorites. I love this topic. This topic had a lot to do with my dissertation when I was getting my PhD. So it has a lot to do with optimization and data analysis, which is very important. So let's go ahead, before we start talking about matrices, let's go ahead and start by reviewing solving systems. So when we solved systems, we were given a word problem perhaps, and we had to turn it into linear equations. So if I look at this example, I have two orders are placed at a pizza shop. Order one small pizza, 2 and 3 salads costing $15. Order 2, 3 small pizzas and 2 salads costing $24. You're to determine how much a pizza costs and how much a salad costs. So you have to define your variables. As I often ask you to do, I ask you to define your variables. So I don't care what letters you choose. Unless I tell you what letters to choose, it's up to you. But I'm asking you to define, let P equal the small pizza, let S represent a salad, or the price of each. How you define it is, up to you. Then we're going to represent each order as an equation. So order 1, 1P, 1 pizza plus 3 salads equals $15. Order 2, 3 pizzas, 2 salads equaling $24. So at that point, I now have my system of 2 equations and 2 unknowns, equation 1 and equation 2. So I represent that as a system, 2 equations taken simultaneously, and perhaps you would use the elimination method to solve this system. So when you're taking a test, I expect you to tell me all of your steps. So my first step would be to eliminate P. If I'm going to eliminate P, what might you do to one or more of the equations to be able to solve this system, eliminate the P? What would you do? I'm sorry? In the first equation. Yes, I'm multiplying everything in the first equation by 3. So I'm going to rewrite my system. My new first equation is going to be 3P plus 9S equals 45. Second equation's 3P plus 2S equals 24. Now, I multiplied by 3, but what would I have to do? What operation to be able to eliminate the P? I'd have to subtract. Now, I could have multiplied by a -3 and added the 2. I'd get the same end result for my values of P and S. So now I've eliminated P, and what do I have left? Nobody's answering my questions. 7S equals 21, because I'm subtracting the entire second equation from the like terms in the first equation. Then I would divide each side by 7, and I'd get the value of S. So S equals 3. But I'm not done. This is a system. I need the value of each equation. So what am I doing next? Substituting. I am substituting. So I'm going to explicitly state that. I'm going to say now I'm going to substitute S equal 3 into equation 1. So I'm going to take equation 1 and I'm going to substitute in 3 for S. So what is P? 6. And so how would I write the solution to this equation? The cost of a small pizza is $6 and a salad costs $3. So you'd have to write your solution as a sentence explicitly answering the question. Now, what if I wanted to represent this as an what's known as an augmented matrix? So here come matrices. So a matrix is just data. It's just an array of data. So if I wanted to write the elements of the matrix. Each of those numbers are entries. They're called elements of the matrix. I can represent the coefficients of the left-hand side of the system of equations as a coefficient matrix A, perhaps as I'll label it. And the way you're going to write that is you're going to look at your rows. So, sorry. This is row 1. This is row 2. So each row represents an order. And then this is column 1 and this is column 2. And they represent the different variables. So if I were to rewrite this system as an augmented matrix, my augmented matrix would be, well, I have in the first order 1 pizza, 3 salads costing how much? $15. My second row is going to be, and that should be order 2. Let me just rewrite that. That's a typo. Order 2. So order 2 consists of 3 pizzas, 2 salads, and it costs $24. Now, when we augment the right-hand side, we kind of draw a line, and it can be solid or dotted just to show that this is data that represents a system. Okay? So this is our augmented matrix that represents this system. This is what's known as the coefficient matrix. So those are just the coefficients. And this is the right-hand side. Now, if you were to describe the dimensions of this matrix, the dimensions of a matrix, we always represent the dimensions by the number of rows, M, by the number of columns, N. So your dimension, also known as your, order of the matrix, or dimensions rather, dimensions, and the order of your matrix is the number of rows, by the number of columns. And it's written with R cross C. How many rows does this have? 2. How many columns does it have? 2. So since the number of rows equals the number of columns, we would classify this as a square matrix. As we can see in this augmented matrix, they are not always square. So if I looked at the order or the dimensions of the augmented matrix, dimensions, like the dimensions of a room, the size of a room, what would the order of this augmented matrix be?
2, 3.
3. So you will have to determine the size, the dimensions, the order of a matrix. You need to know those terms. You need to know that order means dimensions, and it's the number of rows first by the number of columns. Okay? Number of rows, 1 row, second row, 1 column, 2 columns, 3 columns. Number of rows is 2, number of columns is 3. Rows number comes first. Now, obviously, if you're creating an augmented matrix from a system, you want to make sure that your system is written in standard form first. So before you write an augmented matrix, make sure that each of your equations is in standard form, in the same order, or else your coefficient matrix is a mess, right? And not each column represents the coefficients of your system. So let's go ahead and do the first example. What is going to be the order of the matrix corresponding to A? How many rows, how many columns? It is a 2 by 3. Okay, what is the first row? Three, 5, negative 16. What is the second row? 2, 3, negative 9. And you always read them across the row. You don't read columns, you read them element-wise by row. The second one is going to be the same order. But before I write that augmented matrix, what do I have to do? I have to rewrite the second equation. So the first equation stays the same. It doesn't change, but I notice that the second equation is not in the correct order. It is only after that point that you put each of them in the same order in standard form that you write the augmented matrix. Now, we solve systems using different methods. So we are going to use very similar methods when solving a system using an augmented matrix. Instead of doing elimination and substitution, we perform what is known as row operations. You perform row operations on a row, on an equation, on a row, and you can only perform these valid row operations. We'll talk about a few more row operations in a minute, but let's right now talk about these row operations. And they correspond directly to solving systems. You multiply or divide all numbers in a row by a non-zero number. You are add or subtract all numbers in one row to the corresponding numbers in another row. Or you first multiply one or both rows by a number and then add or subtract. Our goal is to take the augmented matrix and turn it into the solution matrix. The solution matrix, this is our goal, if a unique solution exists, is to turn it into this matrix. Now, let's describe what the solution matrix looks like. The solution matrix, which would yield a unique solution, let's say X and Y, an ordered pair, if it exists, is when you have, notice, ones on the main diagonal and zeros everywhere else in the coefficient matrix. So above and below those ones. That is your goal. Your goal is to get the solution matrix, because then we can just read off X equals this number, Y equals this number. Okay, so let's talk about how to perform row operations on this same system to get the same solution that we obtained when we solved it using elimination. So again, when solving, the first thing you want to do is make sure that each equation is written in the same standard form. If not, rewrite it. Are these in the same standard form? Okay, so we're good. So the next step is to write the augmented matrix. So let's write the augmented matrix. 2, 3, 4, 1, -2, 9. Now I will tell you, if any one of those variables is missing, you put a 0 as a placeholder. You can't have an empty space in a matrix. You have to have a placeholder. If nothing's there, it's 0. Now let's talk about how to perform row operations on this. So if I wanted to perform row operations, well, I know what I want. I know I need ones on the main diagonal and zeros on everywhere else above and below those main diagonal entries. But best practice, if nothing is screaming at you, is to get a 0 there. So if I want to get a 0 there, we have to think about what we're doing to these rows to obtain a 0 there. Keeping in mind, this is row 1, this is row 2. So let me just rewrite it and let's talk about how we're going to perform our row operations. So if I'm trying to get a 0 where that 1 is, well, I'll tell you the first step. I would maybe multiply -2 by row 2 and add it to row 1. If I perform this row operation on this row, I'm going to get a new row here. And its first entry is going to be 0. So the way you perform and demonstrate what you're doing is you write the augmented matrix. The row that does not change, or rows that do not change, you draw an arrow. You're saying nothing is changing there. I'm keeping that the same. But this is the row operation. A scalar multiple of row 2, so -2 times row 2, plus row 1. So I'm doing this row operation. Negative 2 times row 2. Negative 2 times 1 is negative 2. Plus 2 gives me 0. And that's, I wanted that. That's the whole point I chose that row operation. Now let's do the same thing to the second element in the second row. Negative 2 times negative 2 is 4. 4 plus 3 is 7. Let's do the same thing to the last element in the second row. What is it going to be? Negative 14. Okay, now at this point, something is screaming to me. I can easily get a 1 where that 7 is by dividing everything in the second row by 7. But let's say it wasn't that obvious. Let's say you didn't think of that. You didn't see that. Best practice, the next thing that you would want to go for would be a 0 here. So I try to get my zeros first. Why? Because multiplying by 0 or adding 0 isn't going to change that element once I add it to another row. So I like to get my zeros first. I personally, if doing this problem, would divide the second row by 7, but again, let's say you didn't see that. Best practice is you go for this 0, and then you go for this 0. So let's think about that. What could I possibly do? I'm not going to change my second row, but what could I possibly do? And I'm going to go ahead and rewrite it, but you would just kind of keep going. But since we're doing this step by step, I'm going to rewrite it. I'm not changing this, but tell me what the row operation I would perform so that I could get a 0 here. Anybody have a row operation?
Minus row 1.
What do you mean minus row 1? I need to get a 0 here. So what would my row operation be? Look at our valid row operations. What can we do?
Could you do 3 minus row 1?
No, that's not a valid row operation. I need to have these to be opposite coefficients, right? So, I mean, I could do negative 7 times row 1 plus 3 times row 2, right? Negative 7 times row 1 would be negative 14 plus, well, 0. So that first entry in the first row would be negative 14. Do you see that? Can you follow this row operation? Okay, I took negative 7 times row 1, so negative 7 times 2 is negative 14. Negative 14 plus 3 times 0 is 0, so negative 14 plus 0 is negative 14. This is the operation I'm performing. Okay, so then I'm doing negative 7 times 3, which is negative 21, plus 3 times 7, which is 21, which gives me, and that's what I was going for, a 0 there. Well, in this case, I had to multiply each row by something and then add them together to get the same opposite coefficients here, right? I'm looking for opposite coefficients here to be able to get a 0 where that 3 is. No, because it has to be a valid row operation. These are your valid row operations you can choose from right now. There are more, but those are the ones that you can choose from right now. Well, I just gave you the 3 valid ones at the top of the page, right? Those are the only things I can do. So let's perform that same row operation on the third element of the first row. Negative 7 times 4 is negative 28 plus 3 times negative 14. Negative 70, you are correct. Oops. Excellent. Okay, so at this point, I have zeros where I need them, but now I need to perform row operations to get ones where I need them. So what can I do to each row to get ones here on the main diagonal. What can I do to the first row? Okay, so you said row 1 divided by negative 14. Or row 1 times 1 over negative 14, right? Okay, so what is my new row 1? 1. What? 0 divided by negative 14. Okay, negative 70 divided by negative 14. You better get yourself some Dinker's calculators because there's so much arithmetic that's going to be going on to these row operations that if you cannot perform row operations and do the arithmetic, you're not going to be able to do the problem. Thank you. Okay, what could be the possible row operation that I could perform on the second row to get a 1 where that 7 is? I'm sorry? Yes, row 2 divided by 7. And you really need to write out your row operations. You will get 0 credit if you do not have your row operations written. So what is my new second row? Okay, at this point, I could take this augmented matrix. I could write the corresponding system, right? If I were to write the corresponding system, this would be x equals 5, and this would be y equals negative 2, right? So I have my solution. My solution is the ordered pair 5, negative 2. And is that what we got for when we solved it using elimination? Yes. Oh, it's a different problem. Yes. So how would I classify this system? It's from the last quest. Thank you very much. Consistent, independent. Because a unique solution exists. Okay. Now, matrices can be used, matrices being the plural of a matrix. Matrices can be used to represent all sorts of data. So I could look at this table of values and I could represent it as a matrix. How would I represent it as a matrix? Well, what would the order of this matrix be? Of the data? What would the order of that matrix be if I were to put that into a matrix? Yes. So the dimensions, it's 3 rows, 4 columns. So my first column is going to be for the year 1980. The second row, so this is year. This is going to be color photos, and these are going to be black and white photos. This is going to be for the year 1980, the year 1982, the year 1984, and the year 1990. That's it. Just representing data as a matrix. Every company collects data, whether it's demographic data on you or sales on you, or the internet collects data on you, the websites you visit, all that kind of good stuff. It's all stored in a matrix, in a database. Now, what if I say I have a polygon, and that each of the columns of this matrix represents a point? Okay, so for example, this would be point P. It consists of the y values -1, correct? The second column is going to represent the point Q, that again has an x value and a y value corresponding to this point. Now, could I have switched it? Could I have written my columns as the x and the y value and my rows as the p and the q? Yes, but I'd have to tell you how I've oriented the columns and the rows and what they represent. So now I'm saying, if I gave you this information And I said the first row represents X values, the second row represents Y values. Each column is a point. Plot the points, connect the points with a line segment. You should be able to look at each of these and say, okay, that's 2, -1. So that's point P in the XY plane. And this is point 2. And then I'd connect them and have the line segment. Again, I'd have to tell you how it was oriented for you to understand the data in the matrix. Now, what if I say, okay, I have a right triangle and I want to represent the right triangle's ordered pairs, values of the coordinate points, as a matrix. Again, I want to have a matrix where I have, well, let me call this A. That's point A. That's point B. This is point C. And they each consist of an X and a Y value. What is the order of this matrix going to be? What is the order of this matrix? 2 by 3. Okay, what is the first row going to be? Well, I'm looking at the X values of each of these points. So what's the first row? The X value for A is 2. The X value for B is, the X value for C is,
Dr. P, you're muted. Dr. P, you're muted. Dr. P, you're muted. Dr. P.
Does she know?
I don't think she can hear us.
And I think everyone in the classroom has their volume off, so they can't hear either. So I don't think anyone but us knows. No one knows.
Someone type in the chat.
I'll do it.
She's been muted for a long time. Dr. P. Dr. P.
I think everyone's muted. Did someone send her a chat or no? Someone,
I said it in the chat.
uh,
Hello.
Dr. V. I don't know about y'all, but my screen's like frozen on the alphabet, like on the graph, like the A B C D E F G.
Same.
But she hasn't written G yet on the graph, so I think it's frozen. Can y'all hear her or no?
No.
No.
Yeah, I can't either.
Can you hear me now?
Yes.
Yes, we can hear you now.
Okay.
Yes.
So let me go. Okay, but you can see everything, right? So where did you stop hearing me?
Like at the right before you started explaining the three-dimensional.
Oh, okay. All right. So we're good right now, right? So you know what we're doing right now? Yes. Do you know what we're doing right now? Wow. And this is why I record my lessons, because when they work, they work. Otherwise, we spend half our time troubleshooting technology. Okay. So can you hear me?
Yes.
Okay. So I have a matrix, and each column represents a point in 3 space. Okay. So this is an ordered triple. So I plotted it here. This is an ordered triple. I plotted it here. So I'm saying each column represents a point. Each row represents the X values, the Y values, and the Z values. Are you with me? So I'm up to point F. I just finished plotting point F. Now I'm going to plot point G. So point G is telling me to go back 2 in the negative x in the x direction, plus 2 in the y direction, and up 2 in the z direction. So that's G. Yes? And then all I have left is H. H is telling me go 0, go right 2, go up 2. So now if points, what shape, I skipped a point. What shape do I have? What is that? It's a little cube. And what is the order of this matrix? Okay, so what's the order of this matrix? Anybody want to tell me the order of this matrix? 3 by how many columns? 8, yes. Okay, so there you have how we use matrices to represent data and how we use augmented matrices to represent a system. So let's talk about how we can solve systems using matrices. Let's go a little bit more in depth into that. So we talked about in chapter 5, in the last chapter, how to solve systems. We said that we can use substitution method, right? And we can use linear combination. So it was also known as addition or elimination or linear combination. And then the other method was substitution. Now there's another method that allows you to compute the exact solution. It is called the Gauss-Jordan method. And then we'll see Gaussian elimination. These are named after people. Now, if you were to solve for the variable, one of the variables in the solution, you could back solve. You could substitute that value into a previous equation, and then you could actually solve for the other variables that way. Well, here we're going to actually take an augmented matrix. We're going to perform row operations in hopes of getting a unique solution, or recognizing at some point that there is no solution, or that there are infinitely many solutions. Now, in this system, I have actually given you the equations in the correct standard form, and I've spaced it out to help you identify the missing variables. You know, on an assessment, I am not going to do that for you. So let's write the augmented matrix. What is the first row? The first row of the augmented matrix. Yes. Second row. Okay, third row. And the order of this matrix? Excellent, 3 by 4. So matrix row operations. Now, we already talked about multiplying a row by a non-zero constant. So I can say A times R sub J, J being any number, any row number. And as long as such that A is not equal to 0, you can't multiply an entire row by 0. And we've already talked about adding a non-zero multiple of one row to another. So meaning I'm adding one row to another row, and I may multiply one of the rows by, again, a non-zero number. Or I may multiply both rows by a non-zero number. The next row operation that we have not discussed is that I am allowed to interchange rows. So if I already have a 1 in that first position in a row, you may want it to be the first row. So you can interchange those rows. That's allowed. So let's talk about how we're going to use Gauss-Jordan to solve a system. we're going to work the first system together using I'm just double-sided arrow saying that I'm swapping the two rows. Okay. So first things first, let's write the augmented matrix. Is it in standard form? Yes, so let's write it. Tell me the first row. Okay, second row. Okay, now, I don't see that I can easily divide each element in a row by a number to simplify it nicely. So the first thing I would go for is trying to get a 0 here. Can anybody tell me a row operation that would allow me to get a 0 there? Remember, I need these coefficients to be opposite for me to add them together. So what can I do to get a 0 where the 5 is? Yes, so 5 times row 1 minus 2 times row 2. Okay, so the first row didn't change. And what is my new second row? Performing that row operation. Take 5 times the value in row 1 and subtract 2 times the value in row 2. What is this first element in row 2? 0. What is the second one? 5 times 3 minus 2 times 4 is what? Yes. And the last element in the second row? No. Anybody? You might as well get your calculators out. I mean, you're going to have to do a lot of arithmetic here. What is this value? Thank you very much. Okay. Now, obviously, I would keep going, right? But I can't keep going. I ran out of space, so I'm rewriting this and saying the next row operation. Now, we know we need a 0. Oops. We need a 0 here, but we also need a 1 here. What do you want to do first? I would. So I'm going to leave the first row alone, but I'm going to say row 2 divided by 7. So first row doesn't change. Remember, you have to show an arrow saying that row is not changing. What is my new second row? 6. So technically, I already know what y is, right? What is y? 6. Okay, but that's not good enough. I have to get the solution matrix. And remember, the solution matrix looks like this for a system of 2 equations and 2 unknowns. So that means I need to get here. How am I going to get a 0 there? What row operation am I going to perform? Okay. Let me just rewrite this. Not changing the second row. I have what I need there. But then I am saying, what am I doing to get a 0 for the 3? Row 1 minus 3 times row 3. Okay, what is my new row 1? (32 minus 18 is what? Anybody? 14? Okay, now what else do I need? I need a 1 here. How am I going to get a 1 there? What row operation am I going to perform? Row 1 divided by 2. You got to show your steps. Okay, so now I have 1, 0, 7, 0, 1, 6. So my solution is the 0.76. Okay, I'm saving this one. You're doing this one on your own after we finish the notes. You're doing this one on your own after we finish the notes. If you want to see the solutions, the completed notes are on Canvas. I'd like to work an example with a 3 equations and 3 unknowns. 3 equations and 3 unknowns. In fact, let's go ahead and jump to this one. That way, if we have time, we can talk about the calculator instructions. So let's look at this example. So needless to say, the previous ones on the previous page you're doing on your own. Okay, first thing first, check to see if they're in standard form. They're all in standard form, so I can write the augmented matrix. Yeah, I don't see that any row contains a common factor other than 1, so I can't simplify any of them. So my first step, now keep in mind our goal is to get a solution matrix if a unique solution exists that looks like this. 1's on the main diagonal, 0's everywhere else, and then these numbers will give us our x, our y, and our z value. So my first step is to try to get a 0 here. So I'm trying to get a 0 there. I'm not changing the first row. I'm not changing the third row, but what is my row operation? What row am I going to use? How am I going to get a 0 where the 3 is? Maybe let's exploit row 1 because I have, 2 1s in there. Anybody?
Row 2 minus 3 times row 1.
That's fine. Y'all both said the same thing, basically. Okay, so the first row doesn't change. The third row doesn't change. What is my new second row? Negative what? No. Negative 4. Last element in that row. Arithmetic. Thank you. Okay, so I have a 0 there. Now there's a couple of things I could do. Or I could just start not seeing those and try to get a 0 here. So if I want to get a 0 there, I'm not going to change row 1. Not going to change row 2, but what is my row operation that is going to allow me to get a 0 where that 1 is? Maybe using row 1. Row 3 minus row 1. Okay, so we said first row doesn't change. Second row doesn't change. What is my new third row? Use this row operation. Come on. Yes. Now, I'm looking at these and I'm thinking I can make each of these rows a little cleaner. Not necessarily the first row, but the second row. What could I do to the second row to make those smaller numbers? Do what? Yes. So I'm going to take row 2 and divide it by what? I'm going to divide by -2, right? Because don't I want a 1 where that first -2 is? Yes. Okay. So what is my new row 2? Okay. What might I want to do to row 3? Okay. If you can work with smaller numbers, do it. Especially if you can get ones and zeros. Now what? What do you want to do? Where do you want to go? Now, personally, I'm looking at this, and I kind of like this. I'd rather have this be row 2. Wouldn't you rather have this row be row 2? That's already in the correct form. I'm going to swap these rows just to show another row operation. So row 2 interchanged with row 3. Well, I mean, whatever value you have a 1 in, if 0 is everywhere else, that tells you what variable you are. So yes, it is now a y. I know y, right? So let's keep going. Let's maybe use row 1 and row 3. Can we use row 1 and row 3? Well, because look at this. And look at this. I already have y. I know what y is, right? Does that make sense? Yeah, but the solution matrix has ones on the main diagonal. Right? So I need you know, I'm already done with that row now. Okay, so now let's go ahead and look at getting 0. You want to get a 0 here? Where do you want a 0? What row am I changing? Okay, so if I'm changing row 1, what is the row operation? I love it. Okay, so this didn't change. This didn't change. So what? What's my new row 1? Excellent. I'm looking like I have two values now. But what do I do next? I don't want to change that row. I don't want to change that row because I have X and Y. Right? So what can I do to row 3? No, you cannot divide anything by 0. That's undefined. I want a 0 here. Not row 1. Not times row 2. Row 3 minus row 2. Right? If I take row 3, 0 minus 0, 1 minus 1, 2 minus 0, 13 minus 3. Are you with me? Yes? Okay. Now what? I'm almost there. I don't need to change row 1. I don't need to change row 2, but what can I do to row 3? To get the solution matrix. Thank you. So what is my solution? The ordered triple? What is the ordered triple? Thank you. Okay, so I want you, we'll talk about calculator instructions tomorrow, entering matrices in the calculator. What I'd like you to do right now is I'd like you to go back, do this problem, and do these 2 problems. and check your answers. Let's do those right now. We'll talk about calculator tomorrow. Yes. Do those practice problems now. The ones we skipped. All the ones we skipped. Let's fix those now, and then I will show you the solutions. So let's work those now. And then, of course, you have on my math lab homework. Yes. Why do I have what? I didn't have, I had 2z equals 10, right? to everyone. You may even get a 0 in a placeholder, and then it becomes a non-zero, and then it turns into a horrible fraction before it all flushes out. It's the nature of your row operations. You can make good decisions or you can make bad decisions in choosing your row operations. And depending on how you choose your row operations, it can get very messy. But ultimately, if you're just doing the right row operations, hopefully you'll converge to understanding the nature of the solution, whether it exists, it's unique, or it's a dependent system.
Dr. P.
Yes, ma'am.
Could I do, for one of my things, I need to do like row 1 plus 1, or row 3 divided by row 1 plus 1?
No, you cannot add a constant. That's not a valid row operation.
Oh, okay.
Are we ready to see any of them? The answers to any of them? Almost. Okay, so if you want to see the answers to any of these to see if you're on the right track, again, row operations are not unique. So the second B and C, you do get unique solutions, but notice you can get improper fractions and you can get negatives. So there are B and C. And then if you look at the first two of the 3x4 augmented matrices for the systems of 3 equations and 3 unknowns, you get a unique solution for the first one, but the second one you get a contradiction, so you have no solution. We'll talk about calculator usage tomorrow and move on. Bye.